Hi everyone, today we're going to be talking about basic trigonometric identities. Now, it turns out that this is my favorite topic in all of trig. However, it usually tends to be students' least favorite topic. I really enjoy it because they're like solving little puzzles, but it's not always clear immediately how to get the answer, and you just really have to play around with these. So, let's get started. In the previous sections, we have studied the trigonometric functions from the geometric perspective. It's time to look at the algebraic approach of trigonometric functions, which is often used in calculus. We need to learn how to simplify and prove or disprove equivalency of trigonometric expressions using identities. These are very important skills that you must build to succeed in calculus. Keep in mind that you need lots of practice because there are different ways to approach a problem, and by practicing it, you will be able to find the shortest way. So far, we have seen the following identities. You need to memorize these, and there is more to come. By the way, what is an identity? So let's look at an equation like x plus 3 is equal to 4. Now, this is an equation where the variable value on the left only has one solution to it. So if we solved this equation, we would get x equals 1. And so this is not an example of an identity because there's only one value of x that is going to make this equation true. Something like x plus 3 squared equals x squared plus 6x plus 9 is an example of an identity because the left and the right thing are always going to be equal no matter what value of x we plug in. So this is not an identity, and this is an example of an identity. But in this class, we are mainly concerned about trigonometric identities, so equations that hold true for trig functions no matter what value for x we plug in. So we have our reciprocal identities here that we've worked with a lot this quarter. We also have our Pythagorean identities, and then these last set of identities we haven't talked about so much, but sine is what we refer to as an odd function because it has the property such that when you take sine of negative x, it is equal to negative sine of x. And cosine has the property where cosine of negative x is equal to cosine of x, and it is an even function. And then lastly, tangent of negative x is equal to negative tangent of x. So tangent is what we call an odd function. Using the Pythagorean identities, you need to be able to recognize that if sine squared x is equal to 1 minus cosine squared x, then we also know that cosine squared x is equal to 1 minus sine squared x. Same with the other two. So in order to simplify a trigonometric expression, sometimes it's easier to rewrite everything in terms of sine and cosine. Another option is to get common denominators. Finally, remember to only use substitution. This means that you must never solve an identity. We're not solving for the x value. Our goal is to try to show that two expressions are equal. Example 1 says prove or disprove that 2 times tangent of x times secant of x is equal to 1 over 1 minus sine of x minus the quantity 1 divided by 1 plus sine of x. So when you are trying to prove a trigonometric identity, you want to usually start with one side of the equation and end up as a final value the other side of the equation. And so generally we'll write either LHS for left-hand side or RHS for right-hand side of the equation. So in this one, I'm going to start with the right-hand side. And earlier we mentioned that One technique that you can do is if one side of the equation has fractions in it, it's often helpful to find a common denominator. So let's see if this will lead us anywhere, but I'm going to multiply the first fraction by 1 plus sine of x over 1 plus sine of x. And then the second fraction, I'm going to multiply that by 1 minus sine of x over 1 minus sine of x. And if we do that, then what we're going to end up getting is 1 plus sine of x minus 1 minus sine of x, like that, over, if I FOIL 1 minus sine of x times 1 plus sine of x, that's going to give me 1 minus sine squared x. Okay, so let's see if we can do some more simplification here. So that was equal to that. And then if I distribute the negative sign, I'll get 1 plus sine of x minus 1 plus sine of x over 1 minus sine squared x. Okay, and then I'm going to go ahead and simplify the numerator. The 1 and the minus 1 will cancel out, and then I can add sine of x plus sine of x to get 2 sine of x over. Now, I'm going to come off to the side here. Remember that our Pythagorean identity says that cosine squared x plus sine squared x is equal to 1. This is a really important identity, and I can manipulate this identity if I subtract sine squared x on both sides. We end up finding that cosine squared x is equal to 1 minus sine squared x. So I can substitute this thing for cosine squared x. And this was based off the Pythagorean identity. I'm just going to put ID for identity. Now, our goal is to get to 2 times tangent of x times secant of x. And it almost looks like we're there. So I'm going to rewrite this as 2 times sine of x over cosine of x times 1 over cosine of x. And basically all I did there was I split up the denominator, and notice that if I multiply these back together, it will give me 2 sine of x over cosine squared x. Now, why did I separate them into 2 fractions that are being multiplied? Well, I know that this thing, based off the reciprocal identities, is equal to tangent, and I know that this thing, based off the reciprocal identities, is equal to secant of x. So now the final thing is I can say that this is equal to 2 times tangent of x times secant of x. And again, that was based off the reciprocal identities. Now, in mathematics, when you complete a proof, there's usually some kind of symbol to denote that you are done writing your proof. And this is the symbol that I use. But sometimes you will also see a square and it's shaded in. So you don't even have to write a symbol if you don't want to. But generally, when you're done with a proof, there's some kind of indication required. Sometimes you'll also see QED, that's Latin, and that also indicates the end of a proof. So I'm just going to stick with this, my little symbol. Again, you can use whatever symbol you want. I feel like a very common one is the shaded in square, and that's a little bit easier to draw, but again, whatever you'd like. So I've started with the right-hand side of the equation, and I ended up here and showed that the right-hand side, when simplified, is equal to the left-hand side. So that completes example 1.